cube root here, so this is just an example. If you want to write it down, you can. We're on page 5. If you want to write it out to the side, you certainly can. This is a simple example. This is stuff you've done before. The cube root of 24. Look at your perfect chart. If you've got cube, what's the perfect cube that 24 divides by? Don't say it out loud yet. Just look at your chart for now. What's the perfect cube that 24 will divide by? If you were gone on Friday and didn't get the yellow one, it's over by the door. Okay, what did you find? What's the perfect cube it divides by?
8.
8, okay, right. So you've done this before. It would become the cube root of 8 times the cube root of, what's 8 times what? 3, right, is 24. 8 times 3 is 24. And now we'll evaluate this one. What's the cube root of 8? 2. So our final answer here, the simplified version of this, is 2 times the cube root of 3. This is just an example. We've done this before. You guys did really well with it. So what we're doing today is we're adding in variables, okay? We're going to do a couple simple examples. Again, you can write these down if you want. You don't have to. So let's take the square root. You got to understand this to understand what we're doing today. It's not that hard. It's just this is not necessarily something you've done before. If I have the square root of x to the 6, for example, you don't see a number in this little index, but what's actually there? It's a 2. This is a square root. It's the most basic root we have. So there's a pretend 2 here. We don't write it in because it's implied, okay? But what you're looking at is the index compared to the number that you have for the exponent. You're trying to say, okay, what is the square root of x to the 6? When we have a square root, we're asking what number times itself twice, or what thing times itself twice. So you're doing x times x is equal to x to the 6. But then think for me, what would the exponent have to be in order to get you x to the 6? Because it has to be the same. Okay, what do you think? It's 3, yeah. X to the third times x to the third. What do you do when you have multiplication? You add them, right? So that gets you x to the 6. Another way to think about it, 2 goes into 6 3 times. That's how I get my x to the third. So the answer to this is x to the third, okay? We're going to do one more kind of like that obviously now we'll do a higher root. This time we'll do a cube root of x to the 6. We'll keep the same number. Again, we're comparing these two things, the index to the exponent you have inside. Because I'm doing cubes this time, now it's okay, what thing 3 times, right? So x times x times x. Think for me, what does the exponent have to be this time to get you x to the 6? So it has to be 2, right? Because then it's x, so 2 plus 2 plus 2 is 6. You add your exponents. This is, yes, x to the 2nd power. Another way to think about it, 3 goes into 6. How many times? 2. I would like to know, what's the shortcut? How do you do this quicker? How do you get my answer to the root faster? We don't want to write this out every time. That would be obnoxious. So what's the fast way to get your answer to a root that has a variable? What do I do with my exponent inside and the index on the outside? What do I do? I'm looking for one word. You just divide. Yes. 6 divided by 2 is 3. 6 divided by 3 is 2. Or you can think backwards. That helps you. 2 goes into 6 3 times. 3 goes into 6 2 times. Yes, you just divide. That's it. So actually, it might be easier than what we've done before, where you don't have to look at your perfect chart for these. You just have to know how to divide. Okay. I'll try and color code. So cube root. Cube root here. This will be the ones that are perfect. And then we'll do another cube root. This will be our leftovers, or whatever other factors we have, okay? That's not a technical term, that's just a term I use. And then we compare the index to the exponent. 3 6. Is that going to work out for us? It is. It's going to work out nicely. 6, x to the 6 is a perfect cube. That's kind of weird to think about because 6 is not a perfect cube, but x to the 6 is because it divides evenly by 3. 3 goes into 6. How many times? 2. Okay, we're not going to evaluate anything yet. Could you when you do this? Yes, you can. I just find we make fewer mistakes if we just split it up like this first because of what you see for the next one. Y to the 5th. Is that perfect? No. Okay. So now you have to think about how many times does 3 go into 5? 1 time, right? 3 goes into 5, 1 time with a remainder of how many? 2. So this is where you now have to split it up. So I'm going to have y to the 3rd, right? Since it goes in 1 time. That one's a perfect cube with a leftover of y to the 2nd. You now evaluate the one on the left. That would give me x squared, y to the 1st, and you keep the one on the right. This is just y squared. Okay, we need to first break this up. We usually break it up into 2 separate roots. So on the top, you've got the 5th root of x to the 10th, and the bottom, the 5th root of y to the 5th, sorry. Okay, so how is this going to work out for you? You can talk to your table. What do you think? Okay, good news for you. These are both perfect, right? 5 goes into 10 how many times? 2, and then 5 goes into 5 1 time. So you get the 5th root of x to the 10th is x to the 2nd, right? Because you're dividing 10 divided by 5, 2. And then on the bottom, the 5th root of y to the 5th is just y. If you want to put y to the 1st, you can. It is just y, though. Okay, and we don't have anything that's still in a root because we were able to evaluate both of them because they were both perfect. So on number 24, you have y to the 5th in the bottom, which is a perfect 5th, right? In the denominator. On number 25 is y to the 9th, a perfect cube. Or sorry, y to the 8th. Wow. I don't know why I said that. Okay, y to the 8th. Is that a perfect cube? I'm thinking about what I would rather it be. I'd rather it be y to the 9th. But it's not a perfect cube, right? Because 3 does not go into 8 perfectly. You can't divide that evenly. At best, right now, it goes in 2 times with a remainder of 2. You could simplify it right now. Usually when I have something like this, I do not simplify it first. I would first rationalize it. So this is what we did last week. So we're going to rationalize first. Rationalize the denominator. Okay, so rationalize it first, meaning that we want to make it perfect inside the root so that you can evaluate it and get an actual answer, right? Because if we try to evaluate this one in the bottom right now, you're still going to have a root there be a cube root of y squared, so that doesn't work out. Okay, so let's think about what we wish it would be on the inside. The closest thing we can make it is y to the 9th, right? So you have 8. How many more do you need? You need 1 more. Because then it would be y to the 9th, right? And then that would do, like, you could take the cube root of that evenly. Make sure you multiply by the cube root of y to the 1st on the top and the bottom. Both sides. You multiply straight across. I'll do this on the next line down. You can't do anything on the top. It's x times the cube root of, you could put y to the 1st. I'm just going to start putting y. And on the bottom here, you add your exponents. So you have the cube root of, this is what we want, y to the 9th. How many times does 3 go into 9? 3, evenly. That's what you need to happen. And so you're doing 9 divided by 3, right? So it is y to the 3rd now on the bottom. So the top, you can't do anything with. It doesn't matter, though. You're trying to simplify it as much as you can. This is as far as it goes. So if you have a denominator that has a radical in it, you need to make sure that you get rid of it. by making it perfect so that you can actually evaluate. That's probably the trickiest one on this page. Okay, remember we're going to split it up into, we didn't do that in the last one because we had division, but this is, we're going to split it up as the perfect stuff out in front. So we'll put the perfects here, and then everything that's left over here. All right, so can you please start with 64? Look at your chart. Remember you have perfect fourths. I understand that 64 is a perfect square. That's not what I'm asking. We're doing fourth roots. So look at your chart. Okay, we want the perfect fourth that 64 divides by. What is it? 16. So we're going to put 16 in the perfect one. Okay, when you divided by 16, what'd you get? 4. So please notice how we split this up. 16, 4. The 16 is perfect. The 4 is not a perfect 4, so it goes on the right. It's your other factor. Okay, so done with that one. So now let's deal with a to the 5th. How many times does 4 go to 5? Once, with how many left over? 1. This is just like remainder division. Hopefully easy. So you're going to put a to the 4th here, but you told me you have how many left over? That goes on the other side. Onward, so done with that. B to the 8th. How many times does 4 go into 8? Twice, evenly. Yes, this is what you want. It doesn't always work out like that, but when it does, we're happy about it. So right now I'm not evaluating anything. I'm just splitting up this stuff that's on the inside. So nothing goes over here for the B's because that's going to work out perfectly for us. And then C to the 3rd. How many times does 4 go into 3? It doesn't. So that has to go on the right side. Because you're not going to like add another C to it. This is not rationalizing in a denominator like we did last time. We're just trying to break this up. So now you evaluate the left side. The perfect stuff, we should be able to find the answer to. What's the 4th root of 16? 2. The 4th root of a to the 4th is a to the, you just divide first. Or think to yourself, how many times does 4 go into 4? Once. Okay, and then the 4th root of b to the 8th is b squared. Okay, this other stuff stays. You can't simplify it, so for a, if you want to keep that 1, you can. If you're doing like delta math, it wouldn't want you to. And that is as far as it goes. If I have the same base in division, what do I do with my exponents? Subtract your exponents. So we're writing down the rule so that way later when you look at your notes, you know what happens. Yes, please do subtract your exponents. There is a 1 on this x. You don't see it, there's 1x there, so the exponent is a 1. Just a reminder that you do not subtract these. That's just division because those are your coefficients. Okay, I'm going to do the first part with you and then I'll have you do the rest. So obviously you get 2. And then you need to subtract the rest. If you need to use a calculator, you can. See if you can maybe do it in your head. This is easy. 1 minus half. 3/4 minus half. You could get common denominators if you want. So I do 1 minus a half. I'm baking and I have 1 cup and I take away a half cup. I have how much left? Half cup. X to the 1/2 power. You can use a calculator, but let's see if we can avoid it. Okay, and then your other one is 3/4 minus 1/2. If you have 3/4 cup, you take away a half cup, you have a 1/4 cup remaining. Maybe it's time to do some more baking if you're struggling with fractions. Okay, so I divided those first two. X to the 1/2 power, y to the 1/4 power. Just a reminder, if you are struggling with your calculator, just ask for help. But certainly you can do this on a calculator if you want. Okay, that's multiplication, right? I have multiplication because there's parentheses side by side. What do I do with my exponents when I have multiplication? Add them. Remember that you don't add these ones. That's just multiplication. 2 times -4 would get you -8. The other ones, though, you are going to go ahead and add. So either with the calculator or by using common denominators. Can you please, you've got x's and you got y's, so add your exponents. And we should probably write down the rule we're using so our notes are helpful later. Add the exponents. Let's see, I'm gonna do common denominators, so 6/3. 2/2. Okay, does that seem right? So I made common denominators by changing the 1 over to 2/2, and 2 is the same thing as 6/3, so I could add those, but they have the same base. I don't care if you use a calculator or not, you just have to know what rule to use and you need to apply it, okay?